regulatory mechanisms along the same direction. And finally, hallmarks are kind of analytic and telling you where we are, while the seven deadly sins are an effort to try to get at therapeutics. And what I want to talk about is slightly different from all those. It overlaps in some ways, but it's about reversal. And not necessarily reversal of damage, but reversal of epigenetic changes. There's no doubt that there's damage, and we need technologies for addressing them. And I can, but this is specifically about epigenetic changes. And here are the rationale. Spokigama and colleagues published this lovely paper in 2013, where they showed that over 25 generations of mouse, you can take an adult nucleus, reprogram it back, send it back through the developmental pathway, and the longevity of the mouse essentially stays rock solid with the normal variation through all these generations of nuclear transfer cloning. So this is telling you that you don't have premature aging or any other defects that everybody seems to amplify ever since Dolly the sheep and it is quite peaceful from mammalian cells that normally would have died in 2 years or so to go on and on in subsequent generations. This shouldn't surprise us. But there are other paradigms in which the aging clock is reset, and probably the one we've already introduced is this one where my 60-year-old cells were reprogrammed from fibroblasts to stem cells and then into differentiated tissues like active fibroblasts or cardiac. And in that round trip, they did not return to a 60-year-old state, but to something much younger in general. Now, the fact that a few markers have changed shouldn't be compelling this transdifferentiation or dedifferentiation. And we might be able to do this with a minimum of light touch. We'd like to do it in situ where the nuclei reside, without having to take them out, make stem cells, or even make stem cells in vivo. We'd like to just change the nucleus itself. So there are a variety of sets of markers that many people in this room are familiar with. That's associated with the gal with the fusion. There's gene expression I already showed you. Fluorescence sequencing is a way of analyzing that in great detail. Telomere length, metabolism, and so on. Two nice articles on methylation as a genesis markers. We work closely with David St. Clair's lab. He's a professor in my department, and he recently published this paper himself on the decline in these gene metabolized NAD+ and ADP rescued by an intermediate precursor to NAD called nicotinamide. And you can see that this kind of rescue in a variety of experimental paradigms where as little as a 2 to 3-fold increase in NAD gives you very significant changes in the age-related decline. Many of you may know this pathway, but for the purpose of this talk, we're going to focus on TFAM, which we're taking in and in up here in the upper left, and it feeds in through SIRT1 down into TFAM, which then impacts mitochondria among the other things. So how are we going to do this? How are we going to do this? So we have a new technology called CRISPR-Cas9, which was brought from bacterial genomes. Now they use it almost every, it's successful almost every organism. It's tried in fungi, plants, and a variety of animals. And in this particular case, CRISPR-Cas9 is usually used for making double-strand breaks, both in nature and also in many experiments. In this case, we're disabling its ability to make cutting and just use it as a DNA binding region to which we can bind activation domain. But we have this integrated into the cell lines. We're in particular going to activate endogenous regulatory mechanisms without actually changing the gene. So if we want to regulate TFAM, we don't have to touch the TFAM gene directly with the DNA. We can act at a distance by making regulators bind to the TFAM promoter and regulate TFAM if we're using activator. We could use a repressor and then measure the kind of biomarkers I talked about earlier, biomarkers of aging, and see what happens. So we want to compare biological or chronological age and alter that. So we're doing this with an associated virus so that we can do delivery to individual mouse cells or systemically throughout the entire body as would be needed for reversal of aging in every cell in one's body. So what we have here is a diagram of CRISPR for those of you who have been hiding under a rock for the last year and a half and have never heard of CRISPR. This is using a guide RNA in red where the DNA is denatured and makes a triple helix. And in this case, we've got these little yellow ball and blue ball things that we have used mutations to eliminate the ability to cut. So that the cutting more just binds. And when it binds, it brings along with it an activation domain, GP64. In fact, we now have, and that's one of the world's best activation domains, we now have an even better ones, but we're just going to focus on this one for this purpose here. We can use that to activate any of these famous genes that you might want to activate and then see the consequences. So we are, in particular, trying to reverse this process of pseudohypoxia that comes from lower NAD or NADH ratios, and we're doing this by upregulating TFAM. This is a mitochondrial transcription factor, and it regulates mitochondrial copy number, among other things. It's shown in previous work that it prevents mitochondrial DNA decline. So these are the map of where we put the guide RNAs for this experiment. So these are CRISPR guide RNAs. CRISPR is tested in many different, this for the cognition of the room that we're following. This is the XT1 of the Cas9. It's not the original one that we published, but the newer one. And you can see activation of TFAM by up to 47-fold. These different guys, you can see some guys have got another, so there's a reason to both computationally and empirically look for the best guide RNA and then use that therapeutically. So this one is the 47-fold one. That's the main one we'll focus on. And we'll use, that's called T2. The T2 guide RNA is the one we'll be focusing on, but we'll use T4 as a control as well as no control. No Cas9 control. So here you can see that not only is the TFAM gene product, the RNA, upregulated, but the ATP is as well. Very significantly above the blank of the Cas9 controls. Furthermore, the NAD plus is up, and the ratio of NAD plus to NADH is up significantly. And again, T2 is the name of the guide RNA. This guiding is made in one part of the genome that guides the Cas9, which is a generic activator for a particular target in the TFAM promoter. And so here's the NAD ratio, NAD to NADH ratio of 7.5. We can look at this in the context of this, in the context of other regulators or other metabolic regulators of this phenomenon. And again, we can see this huge impact of NAD to NADH ratio. So we also can measure the impact on mitochondrial mass, which again is dependent on the guide RNA, as we can see here. and has also had minimal effect on the toxic species. So I just want to thank in particular here Margot Monroe and Bobby Padua, who both of the lab that have really initiated this particular study, John Ock, who has been instrumental not only in running the lab, but in computational biology and design of the CRISPR-Cas9 guide RNA system. The software for this is available on our website, and many people around the world are using it to design their guide RNAs and cancer CRISPR analyses. So I'd like to more than enough time for questions, so please provoke you. Thank you. I have many people to be thankful and institutions as well. This is my conflict of interest slide, and we will be talking about bio-nanotech and comparing it to many other technologies. So from today and yesterday, one gets the impression that this is not really an audience. This is more like a congregation, and we're talking about the search of testable hypotheses. So if you'll open your Kindle to page 241, there's this chart of augmentation, past, and current, where we clearly are no longer natural species. We go much faster in many ways. We've extended our senses and our abilities. In particular, our memory extends more than just a few minutes in some animals for an entire lifetime, thousands of years, and all of written human knowledge available. But there are perils to the kind of exponential extrapolation that many of us here are addicted. This is two curves, actually, in the electronics industry that was one of the dotted lines. And the green curve is the molecular genomics curve. It was predicted that it would take about 6 decades, going on a very aggressive Moore's Law type of exponential, to get to affordable human genome for the $3 billion that I helped initiate in 1984. It could have flatlined when the Genome Project money disappeared. And the lesson that I'm taking is not so much that it's hard to predict the future. It's more about how we connect the dots, not just how we predict the dots, but how we actually bring these exponentials to occur. Unfortunately, this curve did not flatline, as you've seen in one of Ray's slides. It accelerated, and instead of 6 decades, this arrived in 6 years. So I may be one of the few people on the planet that calls Ray Kurzweil a pessimist. And furthermore, I mean, there's a tendency for us to put great faith in electronics. Ray correctly mentioned molecular as the next wave for possibly replacing electronics. We need to get down to small features, and that's where molecules come in. And as part of this revolution, I'm going to show you 2 slides where these are not where the molecular technology is already 6 laws ahead of the electronics. And as you can see from that previous slide, it's accelerating. It's going much faster than Moore's Law, 10-fold per year on occasion, many years in a row, rather than 1.5-fold. And here's an example where the density is higher. In the next slide, I'll show you where the energy efficiency is 6 laws higher. And here we took a book, the Genesis book, and encoded it into digital DNA. And this was about 6 laws better than any of the commercially available consumer storage devices, including flash memory and drives and so forth. And that's density. And you can see me down there in the lower left, actually putting on gloves and doing experiments. That's the fun part of hardware, as you can still do it. Now, this is a progress curve for energy efficiency. And you can see we are making progress at roughly the same rate we're making progress on density of large-scale integrated circuits. But still, there is more than a million-fold gap between what the best energy efficiency is for these circuits and the already high efficiency of molecular devices. You can call these nanorobots, if you will, but these molecular devices like GaN accelerators. I'll show you a couple of examples of what we can do with these molecular machines like GaN accelerators in just a moment. But keep this in mind that we're 6 laws at least ahead, and it's going faster. And here's an example of a molecular computer. Exactly what this person looks like is not quite so relevant as what he did with a molecular computer inside of his brain. And it's not quite so important what he did in such a short period of time. Speed was not the issue, it was the qualitative nature of what he did. This was a huge number of completely paradigm-changing physics papers were written, 5 papers in a little over half a year. And the 2 bell curves there represent that clearly in some regards he is way on the edge of the bell curve in certain computational senses, human computation. What if he were in the middle of the